Okay. 6. As an application of diagonalization process, we have seen what are circulant matrices, right? So in this session, we will see the topic of circulant matrices in details, and also we will look at the eigenvalues and eigenvectors of circulant matrices. Okay. So to understand circulant matrices, the eigenvalues and eigenvectors of circulant matrices, first let us see what are complex nth root of unity. Okay. So it means what? So suppose let us say now omega is some complex number such that omega power n is equal to 1. Okay. So then omega is a complex number whose nth power is 1. Right. So for example, suppose omega is equal to 1, there is nothing to see. So let's start from omega square is equal to 1. So what are the possible values for omega? What are the possible values for omega? For which numbers, if you square, you will get 1? What are the numbers whose square is 1? Such a simple question. Which numbers, when you square, you get 1? Unless you answer, I cannot continue. So is the term complex confusing for you? Tell whatever number you know whose square is 1. Remember, all real numbers also are complex, or subset of complex numbers, so they are also complex numbers. Yeah, only one. Only one. Okay, one is one possible answer. What is the other answer? I square. Uh, I square. What is I square? I square is minus 1, right? And minus whole square is also minus 1. I just want 1, not minus 1. It's such a simple question. Plus or minus 1. What's wrong with you guys? Okay. So it's just plus or minus 1, right? So w square omega square, here omega square is equal to 1 means omega is equal to plus or minus 1, right? So same way, so if you raise it to the power 3, 4, 5, 6, or any natural number, what are all the possible roots? These roots are called the complex nth roots of unity. Okay. So how are we visualizing it? We are visualizing it using polar coordinates. Okay. So we know that any complex number can be written as cos theta plus I sin theta, right? Which is nothing but e power I theta. Now what is theta here? Here theta is given by 2 pi by n. Why is this 2 pi by n coming? We'll see that. Okay, why 2 pi by n is coming? I'll explain it to you. Okay, why theta is 2 pi by n? We will see. So one thing you see that for any integer n, the nth root of unity are given by, so for example, for omega square, how many roots we had? We had two roots, plus or plus 1, minus 1, two roots. Okay, same way omega power 3 equal to 1 will have three roots. Like that, omega power n equal to 1 will have n roots, right? And those n roots are given here. Okay, so k is varying from 0 to n minus 1, so you have n roots. Okay, and where are these n roots lying? These n roots are lying on the unit circle. Okay, and the distance between each of the root is 2 pi by n. Okay, so let us first look at some examples and then we will come back here so that you will have a better understanding. So the nth root of unity are given by points on the unit circle to the angles theta equal to 2 pi k by n, where k is equal to 0, 1 to n minus 1. So the coordinates of these points are cos theta and sin theta. So for example, let's start with n is equal to 2, then you can understand it better. So the two roots of unity are at angles theta equal to 0 and theta equal to pi. How is that? So here n is equal to 2. So theta is equal to 2 pi by n. So what is your theta? 2 pi by 2. N is 2 here. So you will simply have pi. So your theta is pi. It means what? It means you take first root of unity, which is cos 0 comma sin 0. Now you see that it is 1 comma 0. Okay, so theta equal to 0, and after that the next root will appear after pi degrees. So the angle between two roots here is pi. Okay, and the points are 1 comma 0 and minus 1 comma 0. So these are the two roots of unity, and you can see that they lie on the unit circle, and the angle between them is 2 pi by n. In this case it is pi, right? Same way, so let's consider n is equal to 3. N is equal to 3 means what should be your theta? Your theta is equal to 2 pi by n, where n is equal to 3, so it is 2 pi by 3, right? So starting with 0, then you take 2 pi by 3, and then again another 2 pi by 3. So each of this is angle theta. Okay, so 0, and then this angle is 2 pi by 3, and then 4 pi by 3, and then back. So you have only 3 roots of unity, and they are given here. So it is cos 0 sin 0, and here some disturbance. So it should be sine 2 pi by 3. Okay, sine 2 pi by 3. Okay, so this is your second root, and then your third root is cos 4 pi by 3 sine 4 pi by 3. So these are the points here. Okay, so you see that each time you are varying your k. So how is it varying? You see, where was that? Yeah, so omega k is e power 2 pi I k by n. K is varying, right? So for example, in this case, what is your omega naught? So here k is just 0 and 1, right? So what is your omega naught according to this formula? E power 2 pi I k by n is 2. So it is e power just pi I k. So k is 0 here. It means you will have cos 0 plus or comma I sin 0. The coordinates are given by cos 0 comma I sin 0. Okay, which is 1 comma 0. You see how we are getting this 0 here? Okay, so because k is equal to 0, and then when k is equal to 1, you have cos pi sin pi. Okay, same way here also you see that. So here you have theta is equal to 0, 2 pi by 3, 4 pi by 3, because here 0 corresponds to k is equal to 0, here k is equal to 1, and here k is equal to 2. Okay, so how we are getting these three angles, you understand? So you know that your theta varies from 2 pi k by n, where k is from 0 to n minus 1. So here n is 3, so you have 0, 1, 2. Okay, same for fourth root of unity. So now for fourth root of unity, what are the angles you will have? You have 0, pi by 2, pi. Here one angle is missing. Can you tell me what is the next angle? So you would need to have 2 pi k by n, where here n is 4. So you have pi k by 2. So now k is 0 means 0. So k is 1 means pi by 2. K is 2 means it is just pi. So for k is equal to 3, what is the next angle here? What is the next angle here for k equal to 3? Just substitute k equal to 3. What is the next angle? 3 pi by 2. Right? So it is 3 pi by 2. So in every case, the angle is 90 degree here. Okay, and the coordinates are given like this: 1 0 0 1 minus 1 0 and 0 minus. So these are the coordinates. Okay, so here the angle between any two consecutive root is pi by 2, 90 degree. Okay, so now coming back here, do you understand what is going on? Why 2 pi by n? Because the theta here, the angle between any two root is consecutive root is 2 pi by n. So theta is 2 pi by n. That is why here we have taken omega as e power I 2 pi by n. Okay, and here you see that these are the n roots. Okay, and this is the expression for omega power k. This is the expression for omega power k. Okay, so now you see that omega power k is simply 2 pi k by n plus I sin 2 pi k by n, which is exactly this. Right, now what is omega power k whole power n? So it means what? You are just cancelling out this n, so you are simply left with cos 2 pi I plus I sin 2 pi. Cos 2 pi plus I sin 2 pi times of k. Multiple does not matter because you are just going to do the rotation k times, right? So here you are actually having cos 2 pi k plus I sin 2 pi k, and I sin 2 pi k, this is 0 and this is 1, so you get 1. Okay, so this is the general formula for nth root of unity. So what is nth root of unity and what are the roots and where are they on the circle? What is the angle between them? Are all this point clear to everyone? Yes or no? Is it clear? Okay, so if you have doubts you can ask me. Otherwise let's see what are circulant matrices. And okay, before that, what are powers of this nth root of unity we are seeing? Okay, what are powers of omega is equal to e power 2 pi by ni? Okay, so let's see here. Let us consider any positive integer first of all. Okay, what is omega power m? So for example, let us consider omega to be, let's say, third root of unity, for example. So if it is third root of unity, what do you know? You know that omega, let's maybe use fourth unity because you have nice numbers without fractions. So let me take fourth root of unity. So omega be the fourth root of unity. So let's say that omega power 4 is equal to 1. So what is your omega naught, omega 1, omega 2 and omega 3? What are the n roots? What are the n roots? You have 1, right? So when you take cos, here you have cos 0 plus I sin 0, which is 1, right? In the next case, what do you have? What do you have here? Cos 0 plus I sin 0, so this is 1. What about this case? What is your theta? Theta is, remember, 2 pi by n, right? So 2 pi by n, so 2 pi k by n, and n is 4 here, so you have pi k by 2, right? So this is k is equal to 0 case. Now when k is equal to 1, what is your omega 1? So it is cos pi by 2 plus I sin pi by 2. Now what is cos pi by 2? Tell me. What is cos pi by 2? 0. Right? And I sin pi by 2 is, sin pi by 2 is 1. So you have 0 plus I times of 1. So you simply have I here. Okay. Then what about omega 2? Omega 2 means you have k is equal to 2. So if k is equal to 2, what is that you will have? Cos pi plus I sin pi. Now what is cos pi? Minus 1. Sin pi? 0. Right? So it means here you will have minus 1. And the last one, you have k is equal to 3. So here you have cos, here k is equal to 3. So 3 pi by 2 plus I sin 3 pi by 2. Now what is cos 3 pi by 2? 0. And sin pi by sin 3 pi by 2 is minus 1. Right? So you will have 0 plus I times of minus 1, which is minus I. So you see omega naught is 1, here I, here omega 2 is minus 1 and omega 3 is minus 6. So these are the nth root of unity for n is equal to 4. Okay, so now suppose you want to have, let us say, omega power 8. What is omega power 8? Can you tell me? Omega power 8 is for this omega. What is omega power 8? Omega power 4 is 1. So omega power 8 should be omega power 4 whole square, right? What is it? 1, right? Okay. So the same way, what about omega power 4n for, or let's say 4 times of t for any t in n? What is this? It is again 1, right? So it is 1. Okay. Now what about, let us say, omega power 5? What is omega power 5? You know what is omega power 4? What is omega power 5? Yes, it is same as omega power 4 into omega. Omega power 4 is 1, so it is simply omega, right? And omega value is 1. And by the way, do you remember here your omega k is exactly same as omega power k, right? Omega k and omega power k are exactly same. So you can see that this is omega naught is same as omega power 0, or you can say simply omega, or here omega power 1, omega square, and here omega cube. Okay, so omega power 4 is 1. Okay, fine. So, in general, suppose you are having any m, then what are we trying to do? So, for example, here what did we try to do? We wrote phi as 4 times of 1 plus the remainder is 1, right? So, the omega power phi actually reduces to this remainder, omega power 1, right? So, here you see that if m is equal to qn plus r, okay, where r is some number between 0 to n minus 1, then omega power m is same as omega power r. So for example, maybe let's take omega power 7. So what is omega power 7 then? So 7, how can you split 7? 4 times of 1 plus 3, right? So it means omega power 7 is same as omega cube, so which is minus. Okay, is it fine? How are we doing this omega? Is it fine for you? You understand how we are doing it? Yeah. So the same thing you are doing for omega power minus m as well. Okay. So omega power minus m means, so now what we are doing, instead of rotating clockwise, now we are going and earlier we were rotating anti-clockwise. Now we will go clockwise. When there is a minus means, it means we are moving clockwise. So for example, look at this picture. So here omega power r means we have rotated 2 pi r by n angle in the anti-clockwise direction for omega power r. And for omega power minus r, we have rotated in the clockwise direction from 0. From the origin, clockwise direction, the same angle 2 pi r by n. Okay, so we are moving exactly the same angle from origin but in different directions. Here anti-clockwise and here clockwise. Okay, so that is the difference. So here you see that omega power minus m is same as omega power minus r, or you can also write it as omega power n minus r. Everything is going to be the same. So these, whatever we have seen so far, everything is the property of omega, the nth root of unity. Okay, why we have did this, why we have studied all the properties about this nth root of unity? Because we are going to use it for studying circulant matrices. So do you recall what are circulant matrices? If you have a, let us consider, look at the first row here. First of all, what is the size of this matrix? Can you tell me? What is the size of this matrix? Yeah, it is a 8 cross 8 matrix, right? So you have a 8 cross 8 matrix here. Okay, and you can see that, so the first row, you are just shifting every element by one position in the next row by bringing the last element to the first position of the next row. Same way you are moving it again, again. So every time you are moving till you get the first element as the last element here. Okay, so this kind of a matrix is called a circulant matrix. Okay, now for circulant matrix, what is that we know? We know that these are the eigenvectors. So earlier we have seen the same as eigenvector, but only one change. We did not use this y by root n, we just had this. But why is this 1 by root n included? Let us see now. Okay, so for circulant matrix, this 1 omega power k, omega power 2k, etc., omega power n minus 1k is an eigenvector, and if you vary k over 0 to n minus 1, then you get all the n vectors for a circulant matrix. Okay, so for example, here's u dot, u1, un minus 1, all of these are eigenvectors. Okay, so now let us consider this vector here. Okay, so this is the vector we have considered here. Now what is the norm of this vector? Remember, this is a vector in Cn. This is a vector in Cn. What is the norm of a vector in Cn? So for any vector you have, norm is equal to square root of modulus square of each of this, right? So 1 square plus modulus omega k whole square plus etc. So you have the modulus square of each of this term. Now, what is this omega? Omega is a complex number and its magnitude is 1, right? Because the distance of that vector from the origin is 1. It's the nth root of unity. So, it means modulus of omega power m is equal to 1 for all integers m. Yes or no? This point, is it clear? That for all integers, modulus of omega power m is equal to 1. Is it clear? Because it is the nth root of unity, right? So when you take the modulus, you see that this is equal to 1. Okay, for any omega power m, the modulus is equal to m, right? It means what? Each of this term here is 1. So how many ones you are having? N ones. So it means norm of this particular vector is square root of n. So now do you understand why we are dividing by square root of n? By dividing by square root of n, what will happen to this vector now? What can you say about each of this vector now? Norm? What will be the norm of uk for any k is equal to 0 to n minus 1? Tell me, what is norm uk? Because we are dividing by root n, what will happen to the norms? All the norms of the eigenvectors are? See, I have considered the norm of this vector and that I calculated it to be root n. Now, I am considering v by norm v. I have considered v by norm v. Now, what is the norm of v by norm v?
One.
Yeah? What is the norm of v by norm v? It's a normal vector. We have not yet seen it is orthonormal, but it is a normal vector. It means the norm is 1. Right? So what does this mean? This is now a scalar. 1 by norm v is a scalar. Right? You forgot all the properties of norm. Times norm v. So this is 1. Right? So it means that each of this vector here has norm 1. Okay, each vector here has norm 1. Okay, is it clear that each of this vector here has norm 1? So here all the points we have discussed so far, is it clear? I have told for circular matrices, these are the eigenvectors. Note that each of the eigenvector is divided by 1 by root n. What is the reason for it? Because norm of each of this vector is root n. So dividing by root n makes each of the vector and unit vector. Okay, so it is very obvious for k is equal to 0. For the other cases, this is the calculation here. Okay, is it clear so far? Yeah. Okay, if you have doubts, you should ask. Okay, so the next part is that we are going to say that this eigenvector is in fact orthogonal. All these vectors are orthogonal, we are going to say. How are we going to say? So before seeing that, let us first look at this property. What is this property? Sum of these n vectors. Okay, so either it is n if k is a multiple of n, or it is 0 if k is not a multiple of n. Okay, so the sum of all these n roots are n. How is that? So let us consider these n roots. Okay, so now we know that we have assumed that k is a multiple of n. K is a multiple of n means we can write k as m times of n for some integer m. So we see that 1 power omega power m into n, omega power 2m into n, and so on. So every time you have omega power n and then whole power m. So it means each of this term is now becoming 1 because you have n here, right? So now you see that each of this term, omega n power m, omega n power 2m, right? And then omega power n into n minus 1 into m. And you already know that omega power n is equal to 1. So now substituting this, you can see that 1 power any number, it is again 1 only. So you get each of this term to be 1. So you have 1 added n times. So you have this term sum is equal to n. So the first equality, is it clear? Why the sum is equal to n? Is it clear? Yeah. When k is a multiple of n, the sum is n. Now, if k is not a multiple of n, then what happens? Do you all remember what is a geometric series? What is a geometric series? Do you remember? So, a geometric series basically looks like this: a r square, etc. And what is the geometric sum? A plus ar square up to n terms. The first n terms r power n minus 1. So what is this sum? It is a times of 1 minus r power n by 1 minus r, right? So this is the geometric series formula, right? So here, instead of a, you have 1, and then so here you have a is equal to 1, and then instead of r, you have omega power k, right? So a is 1, and then you have 1 minus, instead of r, omega power k whole power n by 1 minus omega power k. But what is omega power k whole power n again? It is omega power n power k, which is again 1. So this is numerator is 1, and so 1 minus 1 becomes 0. So you see that this sum is 0 when k is not a multiple of n. Is it clear? Is it clear that the sum is equal to 0 when k is not a multiple of n? So both the cases, is it clear for everyone that the sum is equal to n when k is a multiple of n and 0 when k is not a multiple of n? Is it clear? Yes or no? Okay, fine. Now we have to see that they are orthogonal. So to see orthogonal, we need to check that their inner product is 0, right? So you take any two vectors, eigenvectors, and we check the inner product is 0. So what is the inner product of any two vectors? So we are in complex space. So you have the inner product defined in this way: 1 dot 1 bar plus omega power k dot omega power l bar, and so on, right? So you have uk comma ul, and the inner product is like this. And what is the conjugate? When you take conjugate, what will happen? Suppose you have omega power k, the conjugate is cos 2 pi k by n minus I sin 2 pi k by n. Now you know that cos of minus theta is cos theta only. It will not change. So instead of cos theta, I have taken cos of minus theta here. and my sine of minus theta is minus sine theta. So I am taking this minus inside here. So now this entire term becomes omega power minus k. So omega power k conjugate is nothing but omega power minus k. So everywhere wherever you have conjugate, you replace the number with the negative of it. Okay, so it means this is what you are getting. Now what do you notice? In the power of omega, every time you have multiple of k minus l. And what is k minus l? K minus l, k and l are some numbers in between 0 and n minus 1. So k minus l cannot be a multiple of n. So if it is not a multiple of n, we already know what happens to the sum. This sum becomes 0, right? So here your k is k minus, instead of k you have k minus l, and it is not a multiple of n, and hence this sum is 0. So what is that we have seen? We see that each of this norm is 1, and we also see that their inner products are 0. It means this set of eigenvectors forms an orthonormal basis. So far you all understood that it is an orthonormal basis? Yeah, that this is an orthonormal basis. Is it clear up to this? Yes or no? Okay, fine. Okay. So for a circulant matrix, we have an orthonormal basis called the Fourier basis, and it is given by this particular formula you have here. Okay. So here we have some problems. Look at the first problem. If omega is the fourth root of unity, then which of the following options is or are true? So here, this statement, when you rewrite, you can write as 1 plus omega square plus omega cube. What is that you already know about the nth root of unity when k is not a multiple of n? So here, in fact, k is equal to 1, right? It is 1 plus omega power k plus omega power 2k plus omega power 3k, where k is equal to 1. And it is not a multiple of 4. 1 is not a multiple of 4. So what can you say about this sum? What can you say about this sum? The sum is 0. Okay, so this sum is 0. So option 1 is correct, and this cannot be correct. Okay, now here, what is the left hand side? You have omega power, omega into omega squared into omega cube, which is omega power 1 plus 2 plus 3. So omega power 6. Now you have omega to be a fourth root of unity. So you can write 6 as 4 times of 1 plus 2. So this is same as omega power 2. What is omega power 2? What is omega 2 for fourth root of unity? We have already actually written what is fourth root of unity somewhere, I guess. Yeah. So omega square should be minus 1. Right? It is minus 1. So option C is correct and D is incorrect. Is it clear? Yeah? Okay. So now the next question, which of the following is or are the fourth root of unity? So fourth root of unity means the power should be, the fourth power should be equal to 1. Now what is I power 4? What is I power 4? You know that I square is minus 1. Right? So minus 1 into minus 1 is 1. Right? So I is the fourth root of unity. What about 1 plus I? What about 1 plus I? So 1 plus I power 4. Let us again split it as 1 plus I square the whole square. Now what is 1 plus I square? 1 plus I square plus 2I. Right? Now this is 1 minus 1 plus 2I the whole square, which is 4 times of I square. So it is minus 4. So is B a correct option or not? Can B be a fourth root of unity 1 plus I? Can it be a fourth root of unity? Yes or no? Option B is wrong, right? Okay, tell me about option C. What is minus 1 power 4? Is it a correct option, option C? Right, it is correct. Minus 1 power 4 is obviously 1. Right? Same way, what about 1 minus I? 1 minus I power 4. You will get a similar expression. From that expression, you can get that it is minus 2I whole square. So again, you have 4 times of I square. The same minus 4 only you will get. So this is an incorrect option. What about minus I? What about minus I whole power 4? Minus I whole power 4 is, again you can split minus I power 2 minus I power 2. So you have I square is minus 1 into minus 1. So again 1. So this is also a correct option. Okay. Is it fine? How are we doing this? Right? Okay. So consider a 6 by 6 circulant matrix M. Which of the following options is or are true? Now for any circulant matrix, is 1 1 1 1 an eigenvector? Yes or no? See, this point we already discussed in the last session also. Yeah, so it is an eigenvector corresponding to the row sum, because for a circulant matrix, each row sum is same. Note that for a circulant matrix, each row sum is same. So in this case, it is H0 plus H1 plus etc. H7. Right? So this is your row sum. So let us call it maybe lambda 1. So you can see that corresponding to this lambda 1 or lambda naught, your u naught, this is your eigenvector. Okay, so for any circulant matrix 1 1 1 or any multiple of this 1 1 1 is an eigenvector. Right? Okay. What about the next point? So you know that circulant matrices are diagonalizable, or so is it diagonalizable or not, first of all? If it is diagonalizable, can you give a reason why it is diagonalizable? What is that we saw in today's session? So if you have a circulant matrix, we have a set of eigenvectors which forms an orthonormal basis, the Fourier basis, right? So here, what is the fact we are using? All circulant matrices have Fourier basis, and this Fourier basis consists of orthonormal vectors. It means what? We are having an orthonormal basis consisting of eigenvectors. Right? So orthonormal basis consisting of eigenvectors. So maybe I'll write so orthonormal set of eigenvectors. Okay, so if we have an orthonormal set of eigenvectors, do we know that M is diagonalizable? Yes or no? Yes or no? If we have an orthonormal set of eigenvectors, do we know that M is diagonalizable? No response. I also don't have to continue. Okay, then complete the remaining problems yourself, and then the next session again, if you respond, we will continue. Otherwise, we can simply keep on winding up the sessions. Okay, so shall we wind up the session then? I guess none of you are interested to answer. So then you should answer, you whether you answer you don't know or whether you answer whatever answer you know. So if you know that a matrix has an orthonormal set of eigenvectors, tell me whether it is diagonalizable. If you don't know, you can simply say you don't know. If you don't respond, then I will feel that none of you don't care about the session. See what is, yes, right? So it is diagonalizable. So what is this diagonalizability in fact? So if you have M is equal to PDP inverse, this P in fact will be an ortho or orthogonal matrix. Whenever you have orthonormal set of eigenvectors, the P will be actually an orthogonal matrix, and hence in fact it is orthogonally diagonalizable. Okay, so it means there is an orthogonal basis of R6 consisting of eigenvectors of M. Right, so all the options are correct for this. What about the last question here? So this is our last question. So listen to this question. So this you have to calculate and tell me. So let me give you all the formulas required to calculate. So let's say A is equal to C naught, C1, C2, C3. The next column should be C1, C2, C3, C naught, and then here again, no, did I do it wrongly? Yes, should be C3, C0, C1, C2, C2, C3, C0, C1, and then C1, C2, C3, C0. First entry now is the last entry. So whenever if you have a matrix like this, what are your eigenvalues? And what are the corresponding eigenvectors? So when k is equal to 0, you have C0 plus C1. So in general it is C0 C1 omega power k plus C2 omega power 2k plus C3 omega power 3k. So this is your lambda k in general. And what is the corresponding eigenvector Vk? Your Vk is 1 omega power k, omega power 2k, and omega power 3k, where your k varies from 0, 1, 2, 3. Okay, so in our specific case, you know that omega power 0 is 1, omega power 1 is I, omega square is minus 1, and then omega cube is minus I. Okay, so now can you calculate all the eigenvalues of this matrix here? Calculate all the eigenvalues of this matrix. So you simply have to take, first of all, tell me what is C naught? What is C naught?
0,
0. What is C1?
7,
C2? 8, and C3?
8,
9. Right?
9.
So now use this and this values given here to get the eigenvalues lambda 1, lambda 2, lambda 3, and lambda 4, or lambda naught to lambda 3. So 4 eigenvalues you need to find by using this formula. So C naught is 0, C1 is 7, C2 is 8, C3 is 9. Calculate and tell me all the eigenvalues. What is the first eigenvalue? Lambda naught. So without even calculating using this formula, can you tell me what is an eigenvalue? Do you remember? I have already given you the hint in the beginning itself. The first eigenvalue is nothing but the, what is the first eigenvalue? It is the row sum, right? What is your row sum here? Is it matching with your row sum? Whatever you have got using the formula and the row sum, are they coinciding? Yeah. So 24 is the row sum actually, right? So your lambda naught is in fact C naught plus D naught. Sorry, there was some connectivity issue from my side. I got disconnected. Sorry. Yeah. So did anyone compute all the eigenvalues? Lambda naught, lambda 1, lambda 2, lambda 3? No one? Okay. So if I am correct, please check whether this is the correct answer. So lambda 1 is minus 8 minus 2 I am getting. Lambda 2 is minus 8 and lambda 3 is minus 8 plus 2i. So did anyone get the same answer? One of you have got minus 8 plus I. So okay. So you have got one of the eigenvalues to be 6. Okay, I have got minus 8. So let's verify this. Please verify. Okay, please check whether it is right or not. Okay, so now with this, let's see whether we are able to answer this question. 1 by 2 I1 minus I1 is an eigenvector of A. So we have not yet computed the eigenvectors here. So we have to compute the eigenvectors as well. So compute the eigenvectors. What is V naught? V naught is obviously 1, 1, 1, 1. What is V1? 1, omega power 1, omega power 2 and omega power 3. So it means we should get 1 I minus 1 I. right? And then V2 is 1 omega square omega power 4 and then omega power 6. So we have 1 minus 1 1 again minus 1, and V3 is 1 omega power 3 omega power 6 and omega power 9. So it means you have 1 minus I minus 1 and here omega, which is I. So these are the eigenvectors. So now this one can correspond to which one? Can you write this as multiple of any one of this vector? So if I multiply minus I, okay, just if I multiply I won't get this. Here if I multiply I, will I get it? It looks like yes. What is I times of V3? It is I 1 minus I minus 1. But anyway, this also 1 and 1 is there, so it is not an option, correct option. So 24 is an eigenvalue, 8 is not an eigenvalue, minus 1, 1, minus 1, 1. Is this an eigenvector? 1, yeah. So it is just the negative of this, so this is fine. So this we see that here at least this should be negative, then it is fine, right? I square means minus 1 is coming. So no, here I square, I'm multiplying minus I square, so it is plus 1 only, yeah. So it is plus 1 and here it is minus 1. So option B and D are correct here. Okay, fine. So finding eigenvalues and eigenvectors, is it fine? So for a circulant matrix, okay, just one thing you should remember that, so this is the just any eigenvector, but if you're specifically asked to find the orthonormal set of eigenvector, then what is it you need to do? You just have to divide by 1 by root 4 here, for example. So you will have 1 by 2 in place of in front of every vector to make it norm 1. Okay, if you're asked an orthonormalized set of eigenvectors or diagonal in the diagonalization you want orthogonally diagonalizable matrix, then you need to consider 1 by 2 everywhere. Okay, in general 1 by root n. Okay, fine. So just one thing I want to mention, I don't know whether that person is here or not. Someone asked about how were we using circulant matrices here. I saw the lecture. In the lecture the circulant matrix was not used at all. Directly eigenvectors were computed, but you can use the properties of circulant matrix and compute the eigenvalues and eigenvector. But don't worry if you are getting a different eigenvector here, because the eigenvectors will be in terms of I. So you can notice that you can obtain one from the one set of vectors from the other set of eigenvectors. So anyway, so for example here these are, let's call this v0, v1, v2, v3. Okay, when you are using the circulant matrix property, these two vectors will be replaced with some other vectors, let's say u1, u2. But you can easily check that span of v1, v2 is same as span of u1, u2, where u1, u2 are the eigenvectors obtained from Fourier basis. Okay, so this is also, please do this homework. Use circulant matrix properties. To find eigenvalues and eigenvectors. Okay, so for this problem, use circulant matrix properties to find eigenvalues and eigenvector. You can notice that you will have different set of vectors for these two, but you can also observe this property that span of one set is the span of the other set. So it is fine if you are getting different set of vectors as well. Okay, what the professor has mentioned is that you have two columns. These two columns are exactly the same. Similarly, these two columns are exactly the same. It means the rank of this matrix is 2. So the nullity must be 2. So you must be having two linearly independent vectors corresponding to the eigenvalue 0. This is what he has mentioned. Nothing more than that. Okay. And I guess that's all for today's session. Hope it was useful for everyone. We'll meet in the next session. Fine. Thank you all. What is that about?